make sure that you understand what the expectation is for the Desmos. Okay, so when you are out, here's our Schoology. If you go to our course, Applied Calculus, each new unit, I'll keep bumping up to the top so that when you log in, you don't have to scroll. I think that's easier. Would you agree? And then I take this conversation and I delete it from whatever the current unit was or the old unit was, and I put it in the current unit. So you okay with that? All right. So then what we decided helps is if I go ahead and I put the homework, and you said that you would like the homework listed as when it's due in the title. That's what you want. It should also show up because when I create it, it should show up in your Schoology as in your calendar, does it? That's why they tell us to take the time. Like this is like six more clicks to create it as an assignment rather than just posting it. But they said if I take the time to do that, you see it in your Schoology calendar. True or false? True. So then we're good. Okay. So here's where the link is. You get entered into my class by taking this link, and by clicking this link. And something that Desmos has done differently this year is I need to allow you access. So is there anybody who tried and was like, you got to wait for your teacher to say yes? Okay. So the cool thing about Desmos is if I look at my summary, I can see everybody that logged in. Oh, this kid didn't start yet. That would be me testing the link. Okay, so here's one of the things that I want to take some time and talk about what we're talking about here, because this has a huge foundational understanding to what we're doing today and for this next unit. So this graph represents the distance time relationship for Carrie as she cycled for the first 17 minutes in a race. Hey, after 17 minutes, if you already did the activity, you don't have to open up your computer. Just give me your attention here. So I go up by my even numbers. So when I'm talking about Carrie in the race at 17, here she is. And I believe that says 5 miles, right? After 17 minutes, Carrie has gone 5 miles. Okay. So true or false, Carrie is cycling at a constant speed. How's that? Not linear. I like that answer. Keep going. What does it mean to be not linear? It's not a straight line, so what do you see instead? Yeah, you see a curve, and when you look at the curve, who's talking to Elaine? So when you see this curve, up comes Carrie, and we're going to pretend like our axis is over here. Okay? So up comes Carrie, and you can see, where is she going faster, here or here? At the beginning or the end of her trip? Yeah, you can see that her speed is increasing. This is in the first couple minutes, right? So we're talking about minutes, distance in miles since the start of the race. Did she go 17 miles in 17 minutes? Did she ride 5 miles? Is that possible? So when I'm walking my dogs, not true. When I'm walking at the gym on with the controls, that treadmill that has the controls, and I'm cooking, I'm going 5 miles an hour. That's how fast I can walk. Now, when I'm walking with my dog, and I'm looking at my Stick with it, right? I can do, it's about 4 miles in an hour, right? So 15 minutes is about 1 mile. Does it make sense that she travels 5 miles in 17 minutes?
Maybe there's an exercise.
Was okay. True or false, Carrie goes at a constant speed. False, because it's not linear. I liked that. Okay. Since Carrie is not traveling at a constant speed, it can be challenging to estimate her speed during the first 5 miles of the race. It is common practice to estimate speed by pretending the speed is constant and asking what constant speed. And then when we talk about that, that's when we get this sketch that we were supposed to do by recognizing that if her speed was constant, my graph would have looked like that. Are we okay with that? That's what it would have been looking like if we were constant. Okay. So that's the hypothetical constant speed, and that's what the sketch looked like. And what do you notice about the two lines? How they're similar, how they're different. They start and stop at the same place, but you can tell this is an unrealistic endeavor for her to immediately start pedaling at this speed that she was able to do when she's hitting her stride in her race. Notice it said it was the first 5 miles, so maybe that's this pace that she's keeping up in what she's doing as we go next. Okay, so when we talk about this, the hypothetical constant speed starts and stops at the same points, so it's an approximation. In order to calculate that hypothetical constant speed, we need to look at the change in Carrie's distance over the change in Carrie's time. Let's make sure we understand what it is we're talking about as far as our axes, because this is representing her distance that she bikes, and this axis is representing her time. And we know that her speed is equal to distance over time. And that speed, we can also talk about her rate that she's going. How fast is she going? What do we call it, a rate? Sometimes I used to tell my kids to remember the phrase dirt. Distance is rate times time. So if I want to know what my rate is equal to, my distance divided by my time. Does all that math make sense to you so far? Yes or no?
Yes.
Okay. So what is the change in her hypothetical distance traveled? And so when we talk about how far she's traveled, that would be 5, right? Are you okay with 5? And if we look at what is the change in her time traveled, you okay with 17? Anybody feeling kind of slopey about that? Change in y compared to change in x? Right, that my distance compared to my time is my rate, isn't slope or rate of change. Are we okay with all these connections to algebra 1? Yeah, okay. Okay, so if the change in Carrie's distance is 5 miles and the change in her time is 17, her hypothetical constant speed, that her rate that she's going along this whole process, is going to be whatever value 5 divided by 17 is equal to. All right. So even though Carrie was not traveling at a constant speed, if we hypothetically assume she was, we can generally summarize her cycling trip. Very nice. So what we end up looking at is an average rate of change over that interval. And you have recognized that to be as our slope, which is the same as a rate of change, and we're going to start calling it an average rate of change when we're looking at the changes in our y's compared to the changes in our x's, which is what we have for Carrie's bicycle trip. The constant rate of change need to stop and start at the same points. Usually the average rate of change is the slope of that straight line passing through the points. So there's that handy dandy slope formula, which we see. Now the interesting thing is, this is what we're talking about taking the slope of, and we recognize, but wait a minute, that's not exactly accurate, hence the study of calculus. We're getting there. The average rate of change is a useful tool for describing a general behavior of a function over an interval where the rate is not constant. So we can practice finding the average rate of change. So then for these values, you are supposed to sketch a line that represents the average rate of change from x is equal to 1 to x is equal to -1, and then calculate that rate of change. So work with me here so you all understand what we're doing. If I have an input of -1, it's right here. And if I have an input of 1, it's right here. So when I'm finding my average rate of change, I am finding the slope of that blue line. Everyone okay with that? So my change in my y's is 4 minus 0, that's 4. My change in my x's is 1 minus -1, which is going to be 2. So my slope or average rate of change would be 2. And you can see that if I do this slope, you can see that, maybe we'll make it green. And we'll do the pencil. You can see that if I rise 1, 2, and run 1, you can see that I can rise 1, 2, right? This was supposed to, hold on. This was supposed to go to 1, like that, right? No, here's 1 here. My goodness. Thank you all. I'm like, why is that not working out? Now we'll change it to purple. Now let's try again. A rise to run. Rise to run. Oh, I like that so much better. So when we talk about an output of 2, a change in my output is 2, the change in my input is 2, my slope is going to be 1. Everybody okay with that? Now sketch a line that represents the average rate of change from 0 to 1. Ready? X is equal to 0 to x is equal to, How much did that change?
Isn't it supposed to be those? Yeah.
There we go. Not that. So we can look at this change, and when we look at the graph, isn't it weird how it's a little bit above, a little bit below? And this represents that average. So that's pretty good, don't you think? Our average rate of change. Change in my y's is 4. Change in my x's is 2. So I have a slope of -2. Calculate the average rate of change of this function over the interval of x is equal to -3 to x is equal to 0. So let's see if I can do this one. 5.1 minus 0, right? Divide by 3, -3. From -2, I input a -2 to 2. So we can have a -2.5 over -2, right? Calculating that and adding that in. Putting those inputs in and doing those calculations. Any questions about that Desmos activity? Because I am going through and grading it, so I want to make sure that you have it correct. Yes. Slide 17. Okay, so when it's asking me to calculate the rate of change of this function over the interval, if I know that an input of -3 gives me an output of 5.1, and I know that an input of 0 gives me an output of 0, when I'm looking at my average rate of change. My change in my y's is this minus this, or 5.1. My change in my x's is this minus this, or -3. So if I divided that out, that would be my average rate of change. Any other questions on the decimals? Okay, just want to make sure we talked about that. To make sure you were all okay with that conversation. All right. Today's unit starts off with a project. The projects are interesting because some of you do them and they end up being a great grade boost. Some of you still have never turned in a project. And what was designed to be a grade boost ends up being a real tanker. So today's project is shorter. That's good. So today's project, hopefully, you'll be able to turn in before you walk out the door. I don't know.
Oh, definitely. My parents would love that.
It doesn't even inspire her. I just what?
Yours is a blue back. Blue, like the blue paper that was inside here. And the one that's in the oh, did I read the what? Oh, that's the top of it. You don't know. What did I write on it? Darn it. Okay. All right, here's how this project works. Here we go. Ready? The project. Did you say no? Is this the one that was on?
This is
Oh, how is that going? Where's the oh, is it bugging you still? No, it isn't bugging me. Is it bugging you still? Come sit here. It's okay. Come sit here. Okay. So today's project goes like this. We're looking at a lot of curves. If there's one thing that the pandemic has given mathematicians is a slew of graphs to look at, right? So we can talk about COVID-19. Let's flatten the curve. Okay. Let's flatten the curve. All right, from what we know about the virus, its spread can change rapidly from day to day, so even looking at the rate of change over a week could give us inaccurate information. So we want to know how quickly is this virus spreading at any given time. Here comes our project. At the beginning of COVID-19, there's a lot of talk about flattening the curve. Many news reports and social media use images like the one below in their discussions. Why was flattening the curve such a big conversation? Take a look at that graph. Yours is a little harder to read, so look at mine. What does that white dotted line represent? And is that a changing value or is that a constant value? Constant. Yeah. Okay. So here's why that white dotted line was a big deal. That was what our healthcare system could handle. So if we have X number of people that are sick, and we have Y number of hospital rooms and ventilators and facilities to accommodate those people, if we have so many more sick, people ended up getting seriously ill and even dying that maybe didn't necessarily have to because they ran out of ventilators, hospital rooms, and supplies. So the conversation about flattening the curve came from, can we change the rate at which this virus is spreading so that we're recognizing it's still spreading, but can we put ourselves in a position of where if we flatten out that curve, then maybe we have the room for everybody that needs the health care. All right. So, what questions do you think people might have asked themselves when they saw images like this? So, when we grade these projects, we are looking for, and I love this word, robust answers. Robust answers are ones that don't just say yes or no. These are answers that tell me why, and I think, and because. So using the word because is guaranteed to get you deeper into what you're saying. Yes, because. I think that this is because. Adding those phrases, now you may max out what your brain comes up with. That is why you're sitting in groups of humans that can help you. So would you please do me a favor and take a look at questions 1 and 2, and I want you to see, brainstorm as many questions of what you think people might think, and then how math can help it out. And mark it set. Go. So it's hard to put ourselves back into where we were 18 months ago, a year and a half ago. This time last year, there's no vaccine. 12 months ago, we were all learning from our living rooms, right? This is terrible. But go back even more, go back 18 months ago, none of us really knew what we were in store for. I mean, can you imagine all of us sitting here with these masks on our faces? Can you imagine all of the restrictions and rules? You know, so when you talk about what questions do you think people might have asked themselves when they saw an image like this, what questions do you have? Talk to me. What questions do you have, Grace?
I put, is the standard for one state or the entire country? I put, what symbolizes the curve A and curve B? What groups do they signify? Is this graph current?
Hey, fellas, can you listen? Thanks.
Is
Go ahead.
this graph current? And how are these numbers?
Yeah. Those are very good thought-provoking questions. Like, who does this represent? Right? Is this just for a state? Is this for the country? Is this for different populations? Like, what are we talking about here? Any other thoughts on your mind? What else are you thinking, Gus? So you want to know if this constant can be, you know, so you must say, okay, well, can we increase the healthcare capacity? Any other thoughts on your mind? Are we talking about a week, a month, a year and a half? When it says time since the first case in the United States, first case in Virginia, first case in Fairfax County. Number of cases, how many cases is that? Who's measuring? Are those positive cases? Are those hospital cases? Are those emergency rooms? Are those people on ventilators? The big thing for me is how much time are we talking about here? Because that's not necessarily clear. Could you use mathematics to answer any of the questions that you listed? I'm curious about how do you want us to flatten that curve? What rate are cases increasing now that we need to get it down to? Do we need to cut our rate in half? Do we need to cut our rate in 2/3? What kind of changes do we need to create for our rate? Okay. So our next conversation comes from, we're going to use mathematics today to explain what was happening with curve A at the beginning of the COVID-19 pandemic. So let's go back up and look at curve A. What quantities are present in this situation? Try to list as many as you can. As a reminder, a quantity is an attribute of an object or situation that can be described. So what factors, what quantities do you think are represented in curve A with your group. Come up with at least 4. Marcus, set, go.
The quantities are like.
What do you think that these could be representing? Like what factors?
Because, I mean, yes, but. The number of
You could also yeah,
oh, yeah.
All right, call out some of the quantities. If other group members list something you don't have, add it to your paper. Name a quantity that you see on that graph. Call it out. Time? Absolutely, time. So time, and we don't necessarily have any idea of how much time we're talking about. Are we talking about from the first case to today? Are we talking like how old is this graph? Another quantity, what do you see on represented on this graph?
Maximum constant. I like just the constant.
Okay, the max out of our constant, which is the constant? The healthcare system capacity. Okay, so there's that line where that is where somebody says we are out of resources, facilities in order to which help you. Okay? What else do you see? What other quantities? Yeah, the number of cases. Is that confirmed cases? What kind of cases? Is that deaths? Is that hospitalizations? Is that people on ventilators? What kind of quantity are we talking about? Number of cases, healthcare capacity, time since the first case. All right, so if you turn the page, your next conversation is, go back to all those quantities that you listed, and with your group, decide, are they constant? Are they fixed numerical values? Or are they changing? Are they varying? Which one of these things changes?
It's not.
So I feel like everything was
It's not.
like
Yeah. Time is varying.
healthcare systems are.
All right, so when we look at number 4, it says for each quantity you listed in number 3, decide if it's constant, non-changing, or varying. Well, it's funny, we already called our healthcare system capacity constant. That's not changing. You know, maybe if somebody passed a bill or legislation to put more money into, we can try to increase our healthcare capacity, but right now it is what it is. So that's going to be a constant value. When we talk about time, that is a changing variable along that x-axis. And then along our y-axis, what we're measuring, that output, that is what we are looking at measuring, how many cases we are looking at. So when you move down to number 5, what you're looking at specifically is, how are we going to flatten the curve? You always imagine somebody just smushing it down, right? But how is that going to happen? And what's going to happen between those values of time and number of cases? So when you go back and you look at that curve that we have, if you look at, I can't necessarily say we have less cases in case B. I don't think case B is any less cases overall. It's just, if we can figure out a way to change what those values of our variables are, can we stay underneath that healthcare capacity? Can we figure out a way to get everybody the care that they need? That's what number 5 is asking you. Number 5 is asking you to go ahead and consider our two varying quantities. Our time elapsed and our number of cases. Can you describe how these quantities are related to each other in the graph? And talk about the difference between curve A and curve B, and what needs to happen in order to get what we need to as an end result. Take a minute and put your thoughts down of what's going on here. Okay, the average rate of change is one way to describe how two quantities vary together. For example, in the exploration you did with Carrie's bike ride, you used the average rate of change to describe how her distance and time traveled changed throughout her bicycle race. The average rate of change was represented graphically by the slope of the hypothetical constant speed. And we reviewed that already. Remember, to calculate the average rate of change, you use this formula. Now, what's interesting is I want you to take a look at the way that we're representing this formula compared to slope. It's kind of like the grown-up version of it, and we'll put both of these versions here. If I have the change in my y values compared to the change in the x, I have y2 minus y1 over x2 minus x1. That's what you saw all through Algebra 1, Geometry, Algebra 2. I don't know about pre-calc. What I'd like you to do is I'd like you to put it into, think about it in function notation, where if I have the output from my second input minus the output from my first input, then I have that change in my outputs compared to the change in my inputs. If this makes sense to you, so should this. When we put it into function notation, sometimes it screws up what kids are looking at because it becomes more complicated. But the reason why we do that is function notation helps us keep track of our inputs, and that's going to be super important moving forward. All right. To better understand how the quantities of time since the first case number of cases are changing together in curve A, we can calculate the average rate of change. According to the Center for Disease Control, there were 30 cases of COVID-19 on March 1st, 2020. We were still in school then. Do you remember the day that they told us don't come back? March 13th, yeah, March 13th. So 30 cases on March 1st, March 30th, 1,000 or 163,539 cases. Use this data as an approximate representation of curve A, assuming March 1st was the first day. There were known cases. That would mean on March 1st, t is equal to 0. Would you in a group please calculate the average rate of change between March 1st and March 30th? Interpret this average rate of change in terms of context. So you mark, set, go. Next up, is the average rate of change you calculated a good overall representative of the relationship between time and the number of cases for curve A? Why or why not? And to help you answer this question, think about what the average rate of change tells you and what does it represent. So whatever number or value that you got, is it fair to say that there are that many cases every day? Is it fair to say that it's pretty close? So what we're curious about is when you came up with that number of cases per day, do you think that when we went from March 1st to March 2nd, we had that many cases? Do you think that we went from March 15th to March 16th, we had that many cases? What do you think about that time that you used in your equation? Do you think your average rate of change that you calculated was a good estimate? I almost said estimation. Estimate or estimation?
Estimation.
It could be an estimate.
I think you were right,
I was combining both words and confusing myself.
but it works. I make it a new word.
Estimation? Tell me what your estimation is. Yeah. What do you think we're going towards here? Is it good or not?
No.
From day 1 to day 2, can you imagine? How many cases per day did you get when you did your average? What do you think about that many per day? Right? All right. So what we want is a better approximation for how quickly the virus spread in the first week using the following information. What makes your approximation better than what you did in number 6? So from 0, so on day 0 we had 30 cases. On day 5 we had 214. Day 10, 1,215. Day 15, 4,000. Day 20, 24. Finally, on day 29, we were up to 539. So what we end up with is a different, when we break that range for our Y values into a smaller value, then we get something that maybe is a little bit more accurate. So instead of going up by over 5,000 cases per day, check it out, we went up by less than 200 in this 5-day span. So if you were to think about it, and do some more calculations, in this 5-day span, 184, did I do my math right?
Yes.
So when you divide that, 184 divided by 5, that's only 36 cases per day. How does that compare to your 5,600? Right? So what you can do for each of these intervals of 5, this one last is 9, check out this one. 163, 539, minus 24, 583. Divide that by 9. This has an average, this by rate is 15,439 cases per 1 day during that interval. That's crazy if you think about the differences. Where this one, my interval was 36 cases per day, right? So the point of this is, when we go to figure out our average, maybe we need to start looking at where we are on the curve and have a conversation about how spread out our information is. From what we've learned about the COVID-19 virus, it spread continues rapidly from day to day. So even looking at the rate of change over a week to give us inaccurate information. Examine the data below from the CDC website. What do you notice about the average rate of change for each of these intervals? With your group, have a conversation, analyze, interact with this data, off you go. Some point